All right. I guess I'll start.
Oh, let me introduce you. So welcome everybody to the America's Rig. We have a great fortune of having Han Dong speak with us today about his project, which is part of his thesis research. He's recently graduated from BU. He's going to be talking about his work in energy efficiency and tuning in the kernel. And this is work that we're continuing to work on in Red Hat Research in the CTO office. So we love to get your input on what you think is interesting and what you'd like to see continued, and what you have questions about after the talk. So thank you, Han. Take it away.
All right. Yeah, so this is work I've been doing with Sanjay Arora from Red Hat and also my advisor, Jonathan Pavu. And yeah, the title is just about just energy efficiency, especially in terms of different kinds of hardwares and softwares. And the goal of this talk is to hopefully provide like a high-level overview of kind of the progress of this research, as well as kind of what are some of the latest findings. And hopefully at the end of this talk, you might hopefully take away with just some message that I have or some finding that might be interesting. So a little bit about me. I defended in January this year, or officially graduated in January this year, and kind of I'm creating a postdoc with BU Red Hat, and kind of my main interests are like in operating system and doing system hacking, as well as doing measurements of systems. That's very interesting. And then think about how we can apply those measurements in terms of enacting some sort of method to improve it. And I'm particularly interested in like looking at, machine learning techniques or other heuristics to kind of improve computer systems in general. And okay, so to start this talk, I'm just gonna kind of give you a simple example of like network processing, how it happens on a single machine. It's a very simple idea. You have a machine, you have your NIC, which is the network card. So that's the device that handles packets coming in. And the basic process is, a packet gets sent to you, and then it's buffered in the NIC, and then at some point there's going to be a interrupt assertion that fires, which is where the hardware lets the software know, hey, you got packets, and that's when the packet gets processed up through the network stack into the application, right? So that's just a very simple example of like a common path length that all packets have to go through. And kind of the question we're kind of interested in exploring is where does the energy consumption happen, right? In this very simple example. And kind of the first is just very simple, which is that if there's no package, and there's no work to be done, your processor is mostly idle. It's just waiting for incoming packets, right? And usually that's what they call these idle sleep states that the processor gets put into, which is where they still consume energy, but it's at a much lower rate. And then the other aspect of where the actual energy consumption happens is actual during when the processor needs to be woken up to do some work. And that's when the CPU is going to be executing instructions at some frequency, right? So basically the clock speed of the CPU determines how much energy your whole machine is going to use, or your socket is going to use. And kind of the next question to ask after this, which is given this very simple example, which is that how can we kind of reduce the energy consumption during this pipeline while maintaining some sort of performance objective, right? And kind of there's, at a high level, you think about this very straightforward manner, there's really two ways, right? One is to increase the amount of time you idle, right? If you sleep longer, that means you're not doing any work, you consume less energy. And the other thing is, what if when you're actually processing the work that need to be done, you actually do it with a lower clock frequency, right? You don't always need to be operating at max frequency always. And kind of, if there are any questions, let me know. Right? And kind of the goal here is right. Can we idle longer, and then can we slow the CPU processing? And kind of what are classes of workloads that can actually take advantage of this? So for example, one common set of workloads are something like web services, right? So any kind of like a database or a Redis server, where every time you access a website, it's going to be hitting some cache that's going to return you like some HTTP pages, for example. And these web services usually have something what they call like a service level objective or agreement, where they guarantee that, like a vast majority of requests, for example, here I'm giving the example that, 99% of the latency, right? When you make a request, 99% of it has to be satisfied within one millisecond. And usually most computers, when you run this, they try to run it in a very high performance mode, where this is trying to like minimize latency while still meeting the SLA. And usually you see this hockey stick graph, where at some point you basically hit the limit of your server because you have enough cores or whatever, and that's when your SLO spikes up. But that's where the load balancers come in to mitigate that. But the key point is that within this area of some load, we're trying to satisfy this SLO, right? The question is, could you actually do something else in there? Which is that maybe you don't want to run as fast. You want to run a bit slower, where you are still under the SLO, right? And obviously you're trading out latency there, but can you actually exploit this little gap to kind of save energy, right? To still support the requests under the SLO, but maybe you don't need to operate as fast. And kind of this leads in kind of what my work has been about, which is that we found that there's actually these two hardware knobs that exist on all kinds of server hardware, which is the interrupt coalescing and the speculative speeds, such that where you can actually reduce the energy that it's using to satisfy some requests while maintaining the SLO. And in particular, I'll just kind of give a brief overview of these two hardware knobs about how they really work. So the interrupt coalescing, it's a pretty common thing across all like network cards. It's basically a hardware value where you can actually write to the hardware device itself, where you say that you set it to some value. In this case, you could say like every 100 microseconds. That would mean that the device will actually wait 100 microseconds before notifying the software that, hey, you have packets to process. So this is a dynamic parameter that gets set. And kind of currently in Linux, or not Linux particularly, but for the device manufacturers that actually make the network devices, they will create their own heuristics or dynamic algorithms to kind of play with this value. And the current dynamic algorithm is basically they look at it on a per interrupt basis. So given some previous interrupt history, they will try to make a prediction about what the next value to set this to. So it's a very dynamic behavior. And similarly, for the processor frequency, almost all CPUs these days have something called a dynamic voltage frequency scaling, and Linux has like a bunch of algorithms to tune that also. And kind of the high level detail of this is just by that equation, which is that the dynamic power that the CPU is using, P here, is a factor of the switching capacitance, the operational voltage, and the frequency. So the frequency is a thing that we actually have access to, right? When they say like a CPU is like 2-point-something gigahertz, whatever, you can actually set that because the hardware manufacturers give you that capability. And by decreasing that frequency, you're decreasing the amount of power that the processor is using. But at the same time, when you're doing that, you're also increasing the amount of time it takes to execute instructions, right? Because your clock speed is going slower now. And also currently, that itself is also being set by the kind of the Linux policy governors in some dynamic way. And kind of our work is kind of is to kind of explore this from a very simple perspective, where we kind of disable these dynamic algorithms, and we're trying to see is there a way we can set this in some like a broader granularity or something that's better than what's available right now to kind of get energy savings. And kind of given these two hardware knobs, one of the first things that we did was that we did this performance and energy study across different kinds of applications. And in particular, we have a very specific measurement problem that we're trying to do, which is that, given some application running on some operating system, you have packets coming in. can we measure what the performance and energy is as we're changing these two hardware knobs, right? The interrupt coalescing and the processor frequency. As we pick different combinations of them, how does it result in the ultimate, energy consumption and also the performance? In particular, we did this on the MLC, given the access to the hardware there, which is we had access to this Intel processor along with this 10 gig NIC from Intel also. And as part of this energy study, we built this whole framework for conducting these studies. So we actually have a modified. We did a small modification to the network card's device driver, where we can capture very fine-grained energy measurements on the order of milliseconds, and on a per interrupt basis. And I think so far this is. I don't think this capability exists yet. So this is something that we built from scratch to do it. And also our logging mechanism creates these procfs files for each core. So you can just cat a file. It'll tell you basically the metrics that it collects. We collect things like instructions, cache misses, cycles, bytes received, etc., and also energy usage. And because it's operating at such a fine-grained level, at the device driver level, it doesn't really matter what kind of applications you're running on top, because it gives you like a unified view of data. And currently it's open source on the website if you're interested in taking a look. And given this collecting framework, we conducted a big performance and energy study. So I'm not going to go into detail of what we found. If you're interested, we have like a archive paper on it. So we did about 340 unique combinations of these, and we collect a bunch of systems data from that as well. And so the graph I'm showing on the left here, so every single dot here is a single experiment that we ran, and the x and y axis are some measurement of energy and some measurement of performance, right? And the different colors corresponds to different kinds of system configurations. So some of them is just Linux running in some dynamic way, and some of them is through our interrupt delay and processor frequency changes. And kind of the big result that we found was that for some particular workloads, you can actually save up to like 70% energy by actually doing this kind of tuning. And kind of a key insight that we found from doing this study is that you can actually see in the figures that these very clear structures of vertical dots, right? The structure delineate very, very stable system behaviors. And kind of the reason we're able to capture this kind of structure in the data is just based off a very simple insight of how the interrupt delay really works, right? So for example, using the same example where there's different kinds of packets coming in, the normal process is that the packets are coming in. It doesn't matter what size of the packet is. The interrupt delay will just pass it up to the application. And kind of the mechanism that we added to actually tune this interrupt coalescing to much wider ranges than what is currently being used is that it instead of waking up the processor every time a packet comes in or etc. We actually arbitrate the layer, right? So by arbitrarily adding this delay, we're buffering more packets before sending up to the application to process, and kind of it has some effects where the first thing is that it reduces the error handling costs, right? Because every time you wake up the software to process this packet, it has to handle the interrupts. Depending on the workload itself, it might consume a lot of CPU cycles. Another thing is by arbitrarily actually just delaying stuff, you can actually prolong the idle period. So like I mentioned before, when the computer is idling, it's consuming energy, but at a less lower rate. And then the last thing is that by being more predictable in terms of the amount of packet data to let the application process, you actually are able to stabilize how much work that the application has to process, right? Because now it comes in a fixed granularity of saying every 100 microsecond, you're going to get a fixed set of packets to process. And what we found is that actually this lets the processor frequency knob to do a much easier job of trading off performance and energy. Because the DVFS knob is the thing that controls how fast the processor is running, So if you are able to give it predictable batches of packets to process, right, it's able to do a better job of like lowering the amount of frequency and lower the amount of energy to process those packets while still maintaining the service level objective here. So this is kind of like basically the big insight that we found from this, and kind of the next steps from this insight that we discovered is that this kind of structure is actually can actually be captured in some mathematical way, and that's kind of where the next part of this work goes, which is that we actually found that you can actually express the data that we collected using a set of mathematical equations that can kind of model this data. And kind of we were motivated to do this was because of the structure that we saw from the study that we did. And kind of the implication here is that because you can actually model the data that you collected, you can actually leverage other techniques to perhaps discover structure in that data. And one class of techniques is like machine learning techniques, right? Where they're very good at getting a bunch of data and discovering some sort of relationship. And so I'm not going to kind of talk too much about the modeling result, but basically we create a set of equations that were able to kind of fit the data that we collected. And basically this then led us to start looking at kind of machine learning techniques which are much more effective than us because the model that we created was kind of limited to the particular application, which was the Memcache server we ran. And also it was limited to the particular hardware we were running. So in order to make this a much more general approach, you can give this problem to a machine learning agent, which is much better at extrapolating structure in the data. And kind of the first steps that we tried to explore in this space was that there are classes of ML techniques called sample efficient ML, where the whole goal is that given some optimization problem, it can converge to some solution in a few samples. So the data that I'm showing here is that we took our existing data and we fed it to this ML algorithm where so every single green dot here is like a unique ITR and DVFS value that we ran from our study. And kind of the X here is a sample that the ML technique took. And kind of the whole point of the ML technique is that given the data we give you, can you find a particular ITR DVFS combination that resulted in the least amount of energy used, right? So this example, so every single cross is a sample we took, and eventually it was able to settle on a solution, which says that it gave us some evidence that okay, maybe now we can apply this technique to data it hasn't seen. And kind of that's where the next part of the work evolved to, where we started applying this technique to like a real world example based on workloads it hasn't seen before. So in this figure, what we did was we built a system where it basically every hour it would like query the energy and the current like latency of a web service that's running Memcached. And we were hitting it with a workload that Twitter released. Basically, it was like an example workload of a in-memory key value store. And this workload was spun over 24 hours. So our algorithm was basically the system we built was dynamically trying to tune the server across 24 hours. And kind of the blue line on the figure on the right, the blue line is basically showing the energy use of Linux, just like a normal Linux, throughout these 24 hours. And then the red bar basically shows the change in QPS values over 24 hours. And then the green one is when we applied our machine learning technique, where it basically dynamically tried to tune the energy use of the server across this time period. And the figure on the right kind of shows where the trade-off is happening, because the figure on the right shows the actual measured tail latency here. So in this case, the kind of SLA we're going for, we're trying to say that 99% of your latency has to be under 500 microseconds, right? So that's where the pink line is for the figure on the right. So we can see that because you can't really express this kind of optimization problem in the current world of Linux policies right now, versus in our technique, you can see that it's trying to make that trade-off there, where the tail latency goes up regardless of the QPS rates, but at the same time you can get massive energy savings. And then the other thing I want to point out is for the Linux Bayesian, right, where you see those spikes in energy usage in the first chunk of each of the graph in the left figure, that's actually the Bayesian process where it was trying to optimize the energy usage. So sometimes they found some bad configuration, so the energy spiked, and eventually is able to settle down to some a better configuration that is able to maintain for the rest of the run. And another interesting thing about this approach is that you can actually express the reward function to this machine learning agent in different ways. So instead of doing, let's say, 99 percentile latency less than 500 microseconds, you can change that number around. So it's a very dynamic method where, depending on your use case, you can actually change the SLOs to meet the customer's or the user's objectives. Right. So that was kind of this was kind of a result that was like a year ago, and kind of after we found this result, the next thing that kind of we actually found is that because the hardware knobs that we're turning are so exterior to both the application and the OS, and they're also in some ways very general, even across hardware. And that's kind of where the next part of this work comes in, which is that we're actually trying to prove that this thing is actually very general, because all sorts of hardware provides a intra-coalescing mechanism, as well as all sorts of hardware or CPUs provide some sort of dynamic voltage frequency scaling. And this is kind of recent work that I've been doing for like the past month or two, which is that we basically expanded our work to include a bunch of hardware. So instead of running it on like the Intel 10 gig NIC and the processor, we're trying to run this on like a 25 Mellanox NIC, a 40 gig NIC. We also have access to some AMD processors, as well as like ARM processor. So and kind of the ARM work is still in progress. We do have some like initial sniff tests that seem promising, but I'm not going to present that right now. And also in terms of software, so before we kind of just focused on Memcached, we actually expanded this to like a bunch of new workloads that are all SLO driven. So some of these are like doing like inferencing in some sense, like handwriting recognition, to something more like classical, like a Cassandra SQL database and like a web search engine. And kind of the main. So I'm not going to go over these in detail because I'm still in the process of like collecting a bunch of data right now and graphing them. But basically, the way I kind of want to show the data is, so the blue bar is kind of just the Linux normally we are running, and we kind of normalize the energy usage to be 1 here, and then the green bar is the amount of savings you can get, right, by using our technique, and for these graphs, these are. It's kind of crazy the way it's organized right now, but there's really no organization, I would say. It's more like different kinds of hardwares with different kinds of apps, and then along within each graph, each set of bars, that corresponds to a different request rate along with a different SLO. So there's a lot of differences here in terms of like what are the workloads that the hardware supports, along with what are the SLOs that it can support. And kind of the whole point that we're trying to prove here is that, this is a very general technique. You can apply it to all sorts of web applications. And we found that, you can get up to 28% energy savings, even in these workloads. And then, so another interesting result that we found is there are actually limitations sometimes of this technique, especially for these set where we actually do a bit worse. So the reason why for that is that this is running on the AMD processors, and the AMD processor only let us set the processor frequencies in 3 values. Versus on the Intel ones, you get like a 16-bit range to set it. So it's 2 to 16 possible values. Here you just get 3. And this is when kind of the ML started, it wasn't able to converge because there wasn't enough dynamic ranges to set the values to. So depending on workload, it actually didn't do as well there. Obviously, there's ways to mitigate it because AMD is releasing a new sets of extensions, I believe, for the processor that like opens up this range more. So that could be something very interesting to explore also. And then the other thing I want to show is actually we also did some quick performance tests. So we also want to ask the question, okay, what if we don't really care about energy? Can we still get performance wins in this case? So in this case, what we did was we basically set the performance governor to be performance on Linux, where you basically that means that it will run the CPU at the hottest. But instead of relying on the dynamic ITR algorithm, we basically did a manual tuning of it to some static value. And the very interesting thing is that we found that across the different hardware and across the software itself, in some senses, very particular ways of setting up this interrupt delay, you can actually boost the performance of the application up to almost 20%. Obviously, this was still kind of like a sniff test that we did to kind of explore the space more, but definitely requires more study because the implication here could be like, because we don't really know when someone deploys Linux or who uses the devices, are they actually are they actually using the interrupt delay mechanism in a proper way? And what we actually show is that you might actually get performance boosts from doing this too. And I think this is partially related to the way the dynamic algorithm is currently working, where it's trying to predict using like the previous bytes received, et cetera, trying to predict what a future value is. But the algorithm is written in some general case, right? It doesn't really adhere to what the particular application needs. So in this case, it might be possible that for your particular application, maybe you don't want it to be so dynamic. Maybe you want it to set it in some coarser granularity. And kind of so the next step. So I kind of broke down after this what are the possible ways we can start like thinking about this problem or like applying it. Kind of short-term things I think about is, could we kind of replace this kind of dynamic, because this kind of dynamic algorithm is something that's more robust, right? And also Linux collects a bunch of system metrics. Can we use other data that it collects to make better decisions over how these algorithms are used? And also, as well as creating some sort of like energy efficient system policies, because currently we only have something called power save, which basically says that it's going to run it at the lowest frequency possible. Can we actually create a new set of policies for Linux where you can do a much more finer granularity in terms of performance and energy. And then the other thing could be something more medium-term goals. So an interesting thing that you might think about next, which I didn't touch, is like the sleep state, right? Because usually when a process is idle, it will select a particular sleep state. And the sleep states usually go from like very shallow sleep state where the cache is still hot until very, very deep sleep states where it will actually flush the cache and stuff. But obviously that's penalty costs there in terms of like waking up the processor, et cetera. So it's a very interesting problem to just expand the interrupt delay mechanism with, what if we let the agent also try to tune the sleep state instead of being dynamic to make that more predictable also. And then another aspect is also just, if we can also try to multiplex different workloads on a single machine, right? Because so far I've just shown that kind of what if you just dedicate the whole machine to one particular workload. But but the hardware mechanism actually enables you to do like a per core DVFS and also per core interrupt delay, right? And can we actually how can we play with those two mechanisms? And also another question could be like, if you have different kinds of web services running and they have different kind of SROs, how could you take advantage of that too, right? And then kind of a long-term thing you can think about is also like, a lot of these, microservices that are running these containers, when you make like a request, usually it spawns like a whole tree of requests that touches a bunch of different containers, right? So really, you can think about this tuning problem in like a distributed system where can you actually coordinate multiple machines in some way to still meet the SLO, but still like reduce the amount of energy consumption. And then the other thing is obviously kind of, so far I've only touched at the processor and the NIC, so especially these days where we have multiple tiers of like in-memory architectures like NVRAMs and SSDs, extra GPUs, and it'd be interesting to kind of understand like kind of in terms of the algorithms that these manufacturers provide with these hardware, are there ways we could do better from a operating systems perspective, because we know more about the applications that are running versus some of the hardware developers who have to create some sort of like general purpose metric. Yeah, and then so this is kind of the end of my talk. Hopefully that was interesting for people. If anyone has questions, I'd be happy to answer them also. All right.
So, Tom.
Yep.
Hello, can you hear me?
Yep.
All right, I just had two questions actually.
Yeah.
The first one being, can the delayed packets lead to packet loss? And what is the relationship between the packet delays and the network reliability?
Yeah. So, because then you're talking about like the TCP timeout. It depends what that timeout threshold is, because on the NICs that I played with, it's on the order of microseconds of how long you can delay this. I guess it depends on how the TCP timeout is set. For example, it's if you, let's say you delay the interrupts for like, I don't know, like 5 milliseconds or something, or even longer, you can definitely, it will trigger retransmits, and in that case, but in that case, yes, it will cause potentially like throughput drops overall. But I guess the opportunity here is the kind of range you can specify, right? You don't need to set it that aggressively. And a lot of it is trying to understand, like, for different applications, what is the proper range you can set it, while not causing packet drops, or like, while still maintaining some performance.
Oh, I see. Then the other question is, your work is mostly on like servers and stuff, yes?
Yeah.
But is it possible to like use this machine learning model or like a version of it to optimize like thermoregulation on edge devices as well?
Yeah, but I guess my answer to that would be the way you frame the problem. Like I would say that the machine learning technique we use isn't like a panacea for like solving a lot of problems. And also, we're not even clear if, especially the machine learning approach we use, isn't even optimized. We just took something from off the shelf. Like, we didn't optimize anything. We took the like tutorial one. They showed us how to use it, and we just stuffed it with our thing. So I would say that, and I would say that probably the main thing that we understood in terms of what makes the ML technique work in this case was that we actually spent the work to do the modeling of the hardware, like in terms of the data that we collected, and given that result was where we felt that this makes sense. And I would say that for energy consumption of edge devices, I think you probably need to do some sort of like measurement analysis first to see whether you can get big wins, and if so, what are the opportunities there to do it.
And Ari Trachtenberg has a question.
Yep.
Yeah. Thank you for the talk.
Mhm.
Very interesting. I had a question. So you're doing machine learning tuning. What is the worst case situation if you end up mistuning, and can that be gamed by an adversary?
Yeah, completely. Like you could totally. So we definitely hit cases where it actually just gave us a bad it gave us a bad value to set it to, which just caused the whole system to just violate the SLA, and that basically rendered rendered it to be a bad result in that case. In terms of gaming the system, I guess if you prep the you can prep the requests that you send, like either if you do it like very low, if you send requests very quickly or something, or you send requests very slowly, you'll probably end up like causing the machine learning agent to kind of like make decisions that aren't that aren't able to adapt to these kind of things as effectively. And yeah, we didn't really look at it, but yeah, but there's definitely some sort of gamesmanship you can do here to play with it.
Thank you.
And Ari, if I can add one more thing to it, the technique we are using is called Bayesian optimization. And the assumption that's being made is that the system is in steady state. So for example, in Han's setup, there's a constant request rate that's coming in from the outside. And if you change the request rate, then at least today we re-trigger the optimization process. And the cost is small because it's very sample efficient, but we still have to re-trigger it. So one of the directions we are following up on is, can we essentially interpolate between solutions at one request rate, at another request rate? There's no guarantee that the solution between those request rates is the average of the solutions, really. But what an adversary could do is, if they had that kind of control, they could rapidly vary the request rate, for example.
Right.
And that would keep re-triggering this process.
Yeah.
And just to continue along that line, so from a systems perspective, it's not really that we're static, right? The point is that we've exposed the decision as to when the right time scale for adaptation should occur. So regardless, for any dynamic algorithm, including the ones that are built into both the device driver and spread throughout the kernel, there is always going to be a hysteresis that you could exploit to cause the system to lose its head. What we have the potential here is to sort of unify that a little bit and take a little more intelligence at how we do that.
Okay. Thank you.
So John Archer asked a couple of questions. I don't know if he wants to clarify about the edge inferencing scenarios. John, do you want to say something about that?
Yeah. Sorry, I think Han was doing a pretty good job trying to address my questions in the chat. But yeah, I did know if maybe I just need to read the paper to understand what hardware you did this testing on.
Yeah.
But I was trying to identify if part of where power consumption matters from some scenarios is where it's solar powered edge computing type of use cases. And trying to optimize the inferencing for like predictive maintenance or computer vision is the type of use cases I'm trying to identify.
I see.
John, just to clarify, when you talk about the inference, are you speaking about the inference the learning that we're doing? Or are you speaking about optimizing the inference that's the application itself?
Yeah, this would be, the inferencing you're doing is to identify what's the best way to run the workload, but then how to take that learning and apply it to a general purpose, YOLO model or TF-like type of scenario.
Yeah, I guess I have to think of, yeah, because yeah, in terms of edge devices, yeah, I mean, fundamentally, if the edge device is running some sort of network job, right, with packets coming in, like because the kind of idea we're trying to present is that, you know, regardless of any kind of network applications, you're going to have this kind of like energy use, right, in terms of idle and also processing. So yeah, I feel like as long as you can express what I've shown here in terms of a workload on the edge device, you know, where they have the similar kind of capabilities, um, I think it should still apply in some sense.
Okay, thanks. Yeah, I'll dig into the hardware in your paper.
Yeah. Also, feel free to reach out to me at my like Red Hat email or BU email.
Yeah, and to further on that, John, so my lab has also done various work at building neural net accelerators for low power acceleration and other aspects. I'm happy to also talk through some of those other interactions from the perspective of the edge.
Okay, all right, thank you. Yeah, there, you know, some of these things are, you know, like machine telemetry type use cases, or you know, places where it's occasionally connected type architectures too. So
Yeah.
there is network optimization to be done based upon what type of topology it's in. So couple different factors there. All right, thank you.
Yep. I think Praveet, had a question.
Yeah, thanks for the excellent presentation today, Han. I have some pretty relatively, I think, simple, potentially softball questions for you. I hope you don't mind. Could you just reiterate to me the actual setup you did on this hardware? Like you talked about putting it in performance profile. Did you also, though, look at things like setting the uncore states and things like that? Because we've heard repeatedly in the field and through our own experimentation that setting the uncore has a significant power performance change. It's something like if you just drop one core state, you end up still at 98. You end up at 98% performance, but you save about 50% power on more recent Intel hardware. Have you looked at any of that when taking this into account, or is that just completely? Like I understand there's only so much you can do, and I don't want. I apologize, Han. I also don't want to embarrass you with that. That's not genuinely not my intent.
Well, I guess when you mention Encore, you mean like the DRAM controllers on the socket, or
no? So there's this concept in you know, past 10 years, I'll say, of the actual CPU core itself, and then the things that they call the uncore. They're all like the components that the CPU really needs, but are not really part of the core, like the L2, L3 caches, the ALU, the FPU. I'm trying to think of what else is over there. There's a whole bunch of junk over there. That's maybe the best way to describe it. Yeah, that is the scientific explanation of saying, yeah, there's a bunch of junk over there. It also has a configurable knob that you can use to put it in a lower state.
I see.
And again, like playing with it just locally as we have, we've seen some pretty interesting results.
Yeah, I've actually never. So the only thing I'm familiar with in that perspective is I do know, like with different sleep states, they start turning off some of these ALU units, right?
Right.
Like, but I don't know. I don't actually know that you can actually programmatically do it. I thought it was in the realm of these like sleep state algorithms and stuff.
It is and it isn't. You can set a lower. You can force it into a lower state if you want to. It's just something to think about as you continue this work. The other thing is that I'm really genuinely curious about is, given the rates of network traffic you did you hit any somebody already kind of touched on this.
Mhm.
Did you end up with any networking timeouts at all given the speed that you were trying to do this at?
Yeah. So the way normally you wouldn't be doing this kind of optimizations at like the peak of
Certainly.
the machine, right?
Yeah.
So obviously we did this during like let's say like 50% of the load or something for that in that perspective. But the thing is, the benchmarks themselves, they basically at the end of it, they generate this thing like the performance of it, which in some sense could be like this is the 99 percentile latency that we measured, and we use that 99 percentile latency to tell us that it's still maintained under the SLO and stuff. That means
Gotcha.
90% of it, right, was fine. Sure, it might be possible that 1% of it like really we did really horribly, but yeah. But in terms of 99 percentile, I was like, okay, as long as we're under that, I think we can accept the energy savings.
Gotcha.
Yeah.
Thank you, and thank you again. Thank you for tolerating my stuff. And again, my apologies. I didn't mean to imply you hadn't done enough. This is a fantastic presentation. I'm the kernel team lead at Red Hat, and
Okay.
I used to be. Well, I'm still technically the x86 co-maintainer for the kernel. So I'm familiar with all this code.
I see.
That's why it's kind of interesting to me to see how
Nice.
you used it to do this.
Okay.
Thank
Yeah,
you. I really appreciate it.
Yeah, I'll definitely look into the thing you pointed out because I didn't know. Yeah, thank you.
Actually, just to push Han a little bit, so this is his advisor, so I get to do that. But in response to that question, actually, one of the cool things is that we actually found when doing this on a research operating system, we found various optimizations where, because, for instance, one of our only accesses to the uncore sleep or the uncore power implications is to use dramatically deeper sleep states, because, for instance, that lets us flush the L3 and turn it off on our hardware. And what we found was there were, like, for instance, in the research OS, where we have very careful control of all the kernel paths, we actually could just keep it in the L3 state as the deep sleep state where we flush the L3s as our only form of idle. And we were actually able to get dramatically better fidelity to this response for power savings. However, that was on very customized OS paths. But something else I think that Han had in his future work is we're trying to look at ways of integrating some of those optimizations as customizations and cut-throughs in the Linux kernel to see whether we can reach sort of those kind of more extremes. And one other aspect that Han did do, he did also do the measurements at the power socket or at the rack level. So we do know that the savings we are reaping are actually having an impact. So it's not that the measure was only on the core itself.
Got it. That kind of adds. So you've played with it a bit. That's all I wanted to know. I'm very politely trying to guide Han in a slightly new direction. Because
Yep.
I think there's going to be impact there. I want you to know, Han. I think you're going to see a significant impact when you start playing with the young core states.
Okay.
We appreciate your politeness. We're looking for that feedback, so thanks a lot.
Oran?
He's Canadian. He can't help it.
So I've been sort of side following this work and a little bit involved, but Han, I guess that there feels, I mean, this is profound. Like, you can introduce queuing and voltage, and in other words, the kernel matters, the optimizations matter for the workload and adapting to it.
Mm-hmm.
If you look at, we've been going down this path for a while of Kubernetes, OpenShift, and sharing among diverse workloads and stuff.
Yeah.
And it feels like you haven't really spoken to that, of the implications from these higher level perspectives, both from the side of what does this suggest about how they should be managing workloads to computers in order to allow for these optimizations, what kind of optimization we want to the machines, and also what would you like to see in Linux, changes to enable further advancements here, I guess, even from that MRT work.
Yeah, I mean, for example, like a lot of, for example, in like data centers, you can imagine like fleets of servers that are configured in certain ways. They're like kind of like the last figure that I showed, right? When you make a request just to get something simple, it touches a bunch of components that are running in like a data center. And you think of it in like a broader scope of like, what if we build a load balancer that takes into this information into consideration, where different machines are configured in different ways that can still meet some sort of SLA, but you're conserving energy, right? And yeah, so I think that's like a very high level like system you can build to utilize some of the observation here. And then the second question was about like, so other than this work out in Linux, we actually implemented this also in a operating system that we wrote in C++, and we have a bare metal device driver where we were able to see the same algorithm applied to it, and we saw some similar savings. And kind of one of the main differences between that operating system and kind of Linux is that there's just way more user bypass in that code compared to Linux. And kind of, so a lot of optimizations that people have done in terms of like, things like MTCP or the UKL work, right? We're trying to bypass a lot of those code paths. The same mechanism could be even applied there. And even there, we saw even more savings because a lot of the instructions there were actually spent on executing the actual application itself versus running a lot of like general purpose OS work. And that I didn't really cover that because I didn't want to like put too many graphs on. But yeah, but yeah, another thing to consider is like, things like DVDK or MTCP and stuff. It'd be interesting to see kind of how we can like incorporate this into their mechanisms for accelerating network applications, but at the same time, can they do it in a much more energy efficient way also? Yep. Arturo, you had a question?
Hello, yes. Thank you for your presentation.
Yep.
Very interesting. Question. I see you use Parrot AR2.0 drones. Can you, well, I couldn't find in the paper how much memory or CPU they use? Just
yeah.
a comment, general comment. Thank you.
Yeah. So usually the machines have like 100 gigs of RAM, of VRAM. So one difference in terms of the results that I showed here is that we actually didn't use a general purpose Linux. We built what we called like a Linux appliance. So it's basically like a stripped down Linux where you have the basic set of system libraries in it to actually run your particular applications. So for example, if you look at the processes that actually this Linux appliance runs, is like 3 times as less as like a normal Linux that boots. And the good thing with this Linux appliance that we built was that it has a custom init.rd. So basically, the file system runs in memory. So and that's how we use that to kind of mitigate like hard disk latency costs, etc. So everything is running from in memory for like the memcached application. And the server had like, I think it was like 100 gigabytes of like DRAM. And we never, I don't think we oversubscribed memory for it for the memcached application. We always just did like a regular deployment.
Oh, okay. So to understand you well, so you basically created a custom image for your products.
Mm-hmm. Yeah.
All right. Awesome.
Yeah, because this was to help because we were doing the study, we really want to isolate like system noise. So we spent a lot of effort trying to clean up Linux basically to get like good system measurements.
Thank you. Cool.
All righty.
And looks like that's all the questions.
Actually, I have one more quick comment.
Of
Just
course,
for those
Jonathan.
who are interested, Han is on the job market.
Yes. Yeah, I'd be happy to talk. things related to energy efficiency or like doing measurements of systems and creating like new heuristics. Yeah, I'd be excited to talk to you guys about it.
Yes, and he's currently still working with Red Hat for a couple of months, so it's easy to get in touch with him.
Yep. 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 All right. I think that's good. Thank you guys for attending this talk and all the great questions.
Yeah. Thank you.
Isn't this the part where we turn the recording off and we tell them what we really think? That's what happens.
I'll do it. That's my favorite part.
Seriously, Han, well done. This was fascinating. Thank you.
Yep. I'm glad. Yeah. Hopefully everyone took away with some message here that I presented.
Everyone laughed at that joke, but Hugh, because he's like, yeah, that's how all Intel meetings or all Red Hat meetings go. Yeah.